This assessment asks us to give the product of the Dieckmann reaction shown on screen. Now we know that the Dieckmann condensation is going to be an intramolecular Claisen, essentially meaning we're going to deprotonate alpha to an ester and have that resulting nucleophile attack another ester. Notice on the left side of the molecule, the ester on the left side over here does not have any acidic protons. So the only protons that can be removed are the alpha protons shown in green. I'm not going to go too much into the mechanism, although we will talk through it. The first step is going to be for sodium methoxide to deprotonate and make the enolate. So we would end up with this enolate after the first step. Now from here, this enolate is going to attack this ester. I will show this because this bond forming steps in cyclizations can sometimes be confusing. How do we make it less confusing? We number our carbons. And so if we number these carbons 1, 2, 3, 4, 5, 6, 7, we see that what we're doing is having carbon 2 attack carbon 7 to make initially a tetrahedral intermediate. What size ring is that going to form? Well, to get from carbon 2 to carbon 7, we have 1, 2, 3, 4, 5, 6 carbons. So we're going to have a 6-membered ring. And so we can begin to draw the product by first just drawing a 6-membered ring. We know 2 through 7 are in the ring, so let's just place those numbers, 2, 3, 4, 5, 6, 7. And from here we can decorate. So notice that at carbon 6 we have 2 methyl groups. Let's put those 2 methyl groups. Carbon 7 had the methoxy group, OCH3, sorry about that. And now O-, that's going to be where our tetrahedral intermediate is. What was attached at carbon 2? Well, the reformed carbonyl and the methoxy group. So carbon 1 and the ester that is present there is what's attached to carbon 2. Carbon 5, 4, and 3, 5, 4, and 3 are just CH2, so we're good there. Now this tetrahedral intermediate is going to collapse down and kick out the good leaving group to give us this product here. And we know that the driving force for these reactions, that in the presence of methoxide, this is going to be deprotonated again. This alpha hydrogen here will be deprotonated to make an enolate again. We can draw this as the enolate that gets made. But we're then going to take this enolate and subject it to the acid quench to reform this. So mechanistically, it's going to go through making this enolate. That's again going to be the driving force for the Dieckmann and the Claisen reactions. We will form this, but then we'll do the acid quench step so that this is the product of our Dieckmann condensation.